This is the Missing Energy Lab, and it was conducted on February 26, 2019. The purpose of the lab was to measure the so-called missing energy of a rolling object. The materials we used were a ramp, books to prop up the ramp, a meter stick, a basketball, a scale, and a stopwatch.
As for our procedure, we first measured the mass of the ball. Then we measured the length of the ramp. Afterwards, we stacked a pile of books up to 26.5 centimeters and laid the ramp on top of it, so one end was on the pile of books and one end was right at the edge of the table. We then rolled the ball down the ramp, measuring how long it took for the basketball to reach the end of the ramp using a phone stopwatch. We then repeated the time measurements and setups at 38.2 centimeters and 46.7 centimeters tall book piles.
Here is our data. To understand the force acting on the basketball while it is on the ramp, here is the free body diagram. The gravity goes straight down and the normal force is perpendicular to the ramp. There is also a force of friction which acts parallel to the ramp and against the motion of the basketball.
Calculations.
To start off our calculations, we will show how initial gravitational potential energy was calculated. Gravitational potential energy was calculated using the equation U equals mgh. The mass of the basketball was found by massing it out on the scale, so we plugged that into the equation. The height was found using a meter stick to measure how far off the table the ramp was, and we plugged that into the equation. Then, we plugged in gravity and came up with our potential energy at the top of the ramp.
Theta was calculated by taking the arcsine of the length of the height of the ramp divided by the length of the ramp. This worked because the ramp above the table made a right triangle where the length of the ramp was the hypotenuse, and the height of the ramp was the side opposite the angle, and sine is opposite over hypotenuse. Acceleration was calculated with the kinematic equation x equals 1/2 at squared plus v naught times t plus x naught, where x is the length, a is the acceleration, v is velocity, and t is the time.
Time was taken using a stopwatch, which we started as we let go of the basketball and stopped when the basketball reached the bottom of the ramp. The speed at the bottom of the ramp was calculated using the kinematic equation final velocity equals acceleration times time plus initial velocity, or Vf equals at plus Vi. Translational kinetic energy was calculated with the equation k equals 1/2 mv squared. We filled in the final velocity, which we found previously, and the mass of the ball, which was found by massing the ball on a scale, and came up with the translational kinetic energy that was gained by the basketball as it rolled down the ramp.
In this graph, we graphed the kinetic energy gained against the potential energy lost. This means the kinetic energy gained was a y-axis, and the potential energy lost was the x-axis. We plotted all 6 points from our data and our neighboring table's data on this graph and found the best fit linear line that went through these points.
The linear equation that we found by graphing the data was k equals 0.6604 u loss minus 0.24201.
The slope illustrates the ratio of kinetic energy gained to lost potential energy. Because of the conservation of energy, which states that the energy of a system can neither be created nor destroyed unless an outside force is acting on it, the ratio should be 1. All the potential energy lost should have become kinetic energy gained, and a value divided by the same value is 1.
The value of the slope is actually 0.6604. This means that not all the gravitational potential energy lost became translational kinetic energy. In fact, a good portion of the potential energy must have become some other type of energy.
The missing energy is mostly going to the rotational kinetic energy because the ball is rotating down the ramp and is overcoming its moment of inertia to do so. Therefore, energy must be converted from potential energy to rotational kinetic energy to move the basketball. Then, also some energy, not as much as the rotational kinetic energy, but still some, is changed to heat energy due to friction.